All right, let's go. Let's go. Okay, 75 minutes. Won't take long. It won't feel like any time passed at all. Okay, so this is lecture 7 out of these the first 8-week block, right? And we have an exam on Thursday. Sorry, but we do. And it's going to be here. It's going to be 75 minutes. It's going to be on everything you have absorbed and enjoyed so far. All right. People are paying money for this, amazingly. That's not working for you? Okay. Let's go. Okay. So, I'm going to tell you a little bit more about LU, right? Kind of race towards the end of that. I need to give you a little bit more information about how that works, because it is somewhat surprising. Like many things that take a while to get through, once you see it, it's obvious. Obvious is a terrible word, so we want to get to the point where you think it's obvious. And anyone should understand this. But that's not how it works, right? So we're going to talk a little bit more about that. Then we'll talk about transposes. And so this is a fundamental symmetry of matrices, which is, right, there are also, you can imagine, so we have pictures. We've talked about how matrices represent pictures. When you take a picture with your camera, now it's a digital picture. So you can think of the symmetries there, you can rotate it, you can do all sorts of things. If you think of that kind of picture, there's a lot of symmetries. But it turns out there's only one symmetry for matrices that we care about, that really manifests mathematically. Okay. And then I'll give you a recap. I'll put some slides up online as well, and I'll go through those at the end that just tells you what's in there. You have, okay, so let's look at some things online. A little tweet fest here. That's usually where things are, so I can talk about that. Oh, look, so things tweet, I forget about this. Totoro friends? No fans? Totoro? Totoro? Yeah, come on. So we were fortunate enough to go to Japan at the end of last year. My kids got to go to Ghibli, to the actual, great. I had to sit in a conference, so suffer. So lecture slides. So there are going to be lecture slides. That second tweet there is a post. So Totoro thinks about matrices as well. Oh, Totoro. The second tweet there is about lecture slides that I'll show at the end of today's lecture, so you can go over those. This is a bit of joyfulness here to do with LaTeX. Don't worry about it, but it makes the math look better. Yes, that's our last lecture from last Sunday, which had all sorts of yips. Last Thursday, all sorts of yips because of the battery problem. And here's the thing. There's a practice exam, so let's go to it. If you have not seen this, there's a practice exam here, and there are solutions to that practice exam. You should do these things, right? You should eat through that exam, practice it, look at the solutions, okay? And figure out what's going on in that thing. I'll do that for every exam throughout the semester, or challenge level. There's your distribution of grades for the second assignment, and I'll hand that back at the end of today's lecture. Put it out, hopefully, in an ordered way, so you can think about that, where you are in that little spread. And what else do we have? Back to this thing. I think we're pretty good. Pretty good. Yeah, so there are some questions about it. So it's going to be Chapter 2, if you have the book, Chapter 2, Sections 2.1 to 2.7. You should know those things. 1.1 and 1.2 are implicit in this, right? So that's things like dot products and so on. You should know that too. Okay, good. And I will try to get today's lecture up, so I know some of you, well, one maybe, look at it and use it later on. That's fine, that's good. I'm trying to help you guys. So I'll try to get that up tonight. It takes about 4 hours to shovel it onto YouTube. Which I don't understand how they can accept these things, but they do. Okay, so, okay, good. Right. Okay, let's have a lecture. These things. All right, so let's go back. I'll give you a couple more examples of LU. LU is not just about square matrices, but we're kind of staying in those a little bit as we go. The next section, we're going to branch out into rectangular ones much more and see what kind of badness happens when we can't solve these problems. We will fully embrace that situation. Okay, let's see. So we had lots of things in front of me. We had an A like this. I'll give you a couple more. Okay, so from last lecture, we got to this magnificent thing, A equals LU. Right, was the achievement. And we saw something a little more about this, which is really, in general, it's PA equals LU, which is an encoding of the idea that you may have to swap the rows of A, right? Swap rows of A first. So if you swap the rows of A in the right way, then you can get this nice triangle story, and it's really rectangle equals a lower triangle times an upper triangle. So you have to be, this can be confusing, what's an upper and lower triangle? A lower triangle has non-zeros below, did I say the right thing? This is a lower triangle, triangular matrix. Zeros up here, zeros down here if it's upper triangular. And I will say this about LU, L is for lower, U is for upper. So that's handy, right? It's not this. It's never this, right? This is bad. You know, so this happens. I've seen it from some of you talking to me that matrices are sliding around. You know, let it do that. You know, let it stick them wherever you like, where it seems better alphabetically. Very important. So we had this example. We had A equals, should I just tell you this? I think so. A equals 1, 1, 1. It's a funny one. 1, 2, 3, 1, 3, 6. And we ended up showing that this is LU with this structure. And it's, I'll write in different colors. So the L is always has part of the diagonal in it. Part of the, I should say, the identity matrix. So it looks like this. Looks like the identity matrix. And then on the bottom, it has the multipliers that we computed. So I'll write them here. There's L21 here, L31. And we did this sneaky thing because of monks coming before us. We made these minus L21s and minus L2s. So it was a bit confusing, but now they're plus. And they're in the right place. This matrix is an L, and its elements are referred to as little l's, right? We do that with big A and little a. So we've been building that story. What did we end up with? We ended up with 1, 1, 2, and this multiplied an upper matrix, upper triangular matrix. Where is it? Let me make sure I've got the right one and I'm not lying to you. I could be lying. Yeah. 1, 1, 1. Yeah, that's right. 0, 1, 2, 0, 0, 1. So this isn't a great example in some ways, and I'll give you a better one. But it does have one attribute. So this is really pivot 1, pivot 2, and pivot 3. They just turn out to be 1s in this case. It's very simple. Right? U has the pivots on its diagonal. And here's an important thing that is clouded by the fact that we have a square matrix. This is an M by N matrix in general, A. This is always a square matrix, square. It's always a square matrix, always is some variation on the identity matrix. And this one is M by N. U is always M by N. So let me say this again. L is a combining matrix. And we'll have more of this when it comes to columns, but U contains building blocks for A's rows. For A's rows. So let me say U's rows are building blocks. Right, so L comes along and combines the rows of L to make the rows of A. And these are simpler rows over here. So let's go back to it. So the idea, so the big idea, is to say again, is to solve two triangular systems. And so instead of A, x equals B, we put in L, so this becomes L U x equals B. So there's a couple of steps. It's great to always write this out so you know what you're doing. This we'll say is equal to C. So we solve this part first. So we solve U x equals C. And this is using back substitution. We did this first couple of lectures. We solve using back substitution. No, did I get that right? No. Sorry. L times C, L times C equals B, right? That's the thing we lift out. So this is an unknown. This is known. This is known. This is known. This is an unknown. Right, so we're using back substitution, so we obtain C. And then we solve, I'm saying the wrong thing. This is forward substitution, isn't it? Yes. Dear idea. And then we solve U x equals C. And that's what we did. This is what we did at the start, using back substitution. All right, so let me tell you a couple more things. It's a recap. I just want to get our brains back in the right space. Mine obviously is struggling. So let me give you another example. There's something about, let me just say this first. There's something about L and U in this case that's special, and A. And it's going to connect into our second part. So what's special about this A? So it has a special symmetry. So it's a square matrix, which is key. A can be, of course, rectangular, but this is a square one, but it's a square one with a special property. The rows look like the columns? Yes, this, yeah. So it's clearer once you have big, yes? Right, so these look the same, and these look the same. Exactly right. So this is good. This is a good thing to add in here. We're going to connect everything in this whole lecture. There's a mirror symmetry here. So I'm going to make a note about this. I'll give you a bigger example. So we observe, this is cool, A equals 1, 1, 1, 1, 1, and then it's a 2, 3, 3, 6, has a symmetry about the leading diagonal. This is a word we use all the time. It's the leading diagonal. Can be confusing in other, maybe if you're using MATLAB or other things, sometimes, you'd think this is X goes this way and Y goes this way, kind of if you were labeling something. But this is, we label rows down this way, right? So this is row 1, row 2, row 3, column 1, column 2, column 3, and there's our symmetry. Right? So we can flip it this way. This thing is called the leading diagonal. There it is, leading diagonal. So, and we'll get a deeper story for this. Someone has lost their questionable fuel. Okay, let's look at L and U. Right, so they're not symmetric like this, but they're flips. They're mirror images. All right, about this diagonal. So that's very good. All right, so, and L and U are mirrors of each other. All right, so we'll come back to this. Around this leading diagonal. Right, so we can say we flip, if you want to destroy the housing market, we flip L to get U, and vice versa, right? So these two facts are connected to each other very cleanly. And we'll come back to that in a second. I'll give you some more examples. So let's see, is this a good example? It's okay. All right, so we're not going to calculate this one. I'll tell you the answer. So here's another example. And let me just add here. Is there a question? Or nope. The power of this is if you're going to use A over and over again, it describes your nuclear reactor or how comics work or whatever it is, or the internet or something. If you're going to use it over and over again, you're going to change this thing. Right? So you're using the same orchestra to make different music, then it's good to kind of break your orchestra down. Right? So it's useful to store the orchestra as L and U. So you have all the components, and then it's going to be easier to solve this thing, unless you're Mozart and you just do it. Right? And you're crazy, and Salieri goes berserk. All right, so, but that's the big, these things are simple to solve, these forward and back substitutions. Yep, okay. Okay, let me annotate that. It should be here in your notes, I guess. So, easier to solve, AX equals B if B changes. Changes, A fixed, right? And again, I'm going to put it here. I'm going to put it here. So this is your orchestra, and this is your sound. If you want beach balls and palm trees or something that, I don't know, yeah, okay. That sing, right? That could be your orchestra, singing beach. Okay, that was just weird. All right. Not as weird as the decision not to run the ball. But anyway, okay, so, I mean, Australian rules football, you know, okay, all right. Sorry. Okay, good. So let's do another example. This is going to be different. It's not a symmetric thing to start with. So here's A, and I'm just going to give you the answer. 2, 2, 4, and we'll look at the anatomy of the, I like to say that word, probably erroneously, 3, 0, 13. Let's see if that's actually true. Equals, and if you break this character down, you get, again, you get different color, whatever the color is. We get 1, 1, 1, 0, 0, 0. This is m by n. Again, this will be m by m. Of course, these are all 3 by 3s, so different color. So that structure's all there, and then we get, let's see if this is right, 1, 2, minus 1, and 2, 1, 3. 0, minus 1. This is pre-solved. It comes in a box. It's on the back of a Pop-Tart box. 0, 4. Okay, so we have this. So again, let me put that in. L always looks like this guy. Always has that structure there. The 1s. This is always upper triangular. Let me do it like that. So there are a couple of things here. This one is a more interesting U. I mean, I'm sure it's fascinating to you, but this is L, and this is U. This is more interesting. It has pivots. So here's the thing to do. Write down the 3 pivots. D1, D2, D3. Write down there are 3 multipliers here, L31 and L32. Write those down. All right, so once you've got in this form, you can see it. The pivots are just sitting here on U. They are 2, -1, and 4. And we have 1, 2, -1. 1, 2, -1. Now, so these pivots are more interesting, right? This one over here didn't have, the pivots were all 1, so that was a bit unusual. Here is anything else I want to say about that? It's okay. So here's one more step that people will take. And this is a terrible notational disaster. I mean, LU is not very exciting already. But so we also see this, use this form. Use the form, I'll put in brackets here, it could be PA, that's always true. LDU. It's a different U. This is just ridiculous. Okay, this is terrible. This is a different U. It's still upper triangular. And this is a diagonal matrix, M by M matrix with the pivots. This is actually this is a much nicer kind of factorization. So many of the ones we'll come across will have 3 matrices. And in this case it would be, so example would be L stays the same. This really is terrible notation. It's a different, now we've got a different, this is going to be D in the middle. So A is L, there's a D matrix and a U matrix here. So, diagonal matrix, right? Zeros everywhere except the diagonal. So I want to make the pivots really obvious. I want to pull them out and show you what's inside this machine. Right? So the pivots are 2, -1, and 4. So can we do this? This is a nice thing to... Right? We'll come back to this as we go through the course. Diagonal matrices are awesome. They're the best. And many matrices have a diagonal matrix living inside them. You just have to look at it the right way. All matrices are special, but some are more special than others. Okay. 2, -1, 4. So we could do that, but we have to extrude it from this matrix. Yeah, so that's exactly what, well, that's going to happen. Good point. So we're going to end up, chalk, committed suicide. Okay, 1, 1, 1. That's always going to happen in this case. 0, 0, 0. So it starts to look like the flip of L. So we have the 1s here, the 1s here. But let's sort of go back and try to make this U over here. It's just terrible that this is how we do it. So 2, 0, 0. So we'd have to double this line to get to this one. Or you could think of pulling 2 out of here. So you're going to halve this. You're going to halve this row. So it'll be a half, and then 3 halves. So I want you to think about matrix multiplications not being a whole bunch of dot products. I mean, it is that, but then this kind of lifting into bigger ways of calculating. So 2, 0, 0. What does that row do to this matrix? It says, I want 2 of the first row, 0 of the second row, and 0 of the third row. So 2 of this row makes a 2 here, a 1 here, and a 3 here. And we're back to this. I can't, it's an indefensible notation. You just can't do this. I mean, it's terrible. These U's are different. You just say from the outset, we're doing LDU factorization or LU factorization. But it's what humans have done. They're bad people. Okay, so this is a pivot. It's -1. We've got our -1 here. So we want to divide that row by -1. So it's just this guy. Right? So 0, this says I want 0 of the first row, 0 of the third row, and -1 times that second row. So 0 times -1 with -1, -3. Boom. And then I just want 4 of the last row, and that's going to be 4 of that. So this is a more elegant looking factorization, which we're psyched about. And the pivots which are cool, they're cool, they're not as glorious as eigenvalues. We'll get to those guys. Yeah. But they're like super hard to get to. And crazy. Okay, so that's a different way of doing it. Right? And I'll give you one more example. Will I give you one more example? Let's see if I can fail to do that. Oh, good. Okay. Okay. So we okay? Bad? Our lives are hard. I know we're doing this. But last night the water main broke on our street. So they're out all night, -6 or whatever, digging up the road, trying to find, and they still haven't found the, man, that really does suck. These people are heroes. Anyway. We get to struggle through this. Let's, you know. Let me give you one more example, and it will connect back to the symmetry thing. We didn't have it before. Let's see. So this is a, what have I done with myself? No, that's not right. Here, this one. All right. Let's have a, this is possibly true. I figured it out last night. So -2, -4, oh, sorry, 4, -6, 4, 5, 32, -6, 32, 65. Little bananas. So it's easy to make a matrix that has a particular L and a U. You just dream them up and multiply them together, right? So you can do that. It's harder to find L and U. Important point. What is this matrix? This is one of these super cool matrices, right? It has this symmetry. We note awesome symmetry. And the thing we noticed before, right, was that L and U were flips of each other. Yes? But that was actually a bit special because the pivots were all 1. So that was kind of shaky. So let's get this character. So in fact, it turns out to be like this if we do our LDU, right? So LDU decomposition. So LDU, it's going to be minus, and I'm just giving you the thing, you'd suffer through this to get it out. 1, and the pivots are -2, 5, 3, 0, 0, 0. And then 1, -2, 3, 0, 1, 4, 0, 0, 1. So here's pivot 1, pivot 2, pivot 3. Let's label them all again. So this is L21, L31, L41, L32. Brain. 1's on the diagonal, 1's on the diagonal. It's very nice. And L and U have this, they're mirror images. So the symmetry of A is reflected in L and U being mirror images, mirrors about the leading diagonal. And we've got one more thing to do with LU, and then I will get onto these things, but here's the notation we'll use. We'll say A notation, this is coming, is A equals A transpose. So we write a little T up here. And in this case, L equals U transpose. So we'll get to this. This is next. This is after the advertisement. All right. About a puppy dog. Okay. Loctite. An ad about Loctite. That was pretty good. Okay. Okay. So, now why does this always work? All right, and I kind of blasted this little piece out at the end of last lecture. How are we doing? No, so generally speaking, the game is you take an A and you break it into LU or LDU, depending on what your world is. I just want to show you a few examples of where you get to after all the suffering and the kind of things you could get. Yeah. So suffering minimization. This is after the suffering. Yeah. So just pretend you suffered a lot, and you've got this majestic thing in front of you, and now we're just enjoying it. So, okay, last thing. So why can we do this? Why can we find, and in general, it's PA equals LU. Why can we do this? So let me just try to appeal to, it's just sort of we'll go through this kind of 3x3 story that we've had. And I have these things everywhere. So let's think about how do we make U? Yeah, so I was trying to show you where you could end up. A couple of cases you can end up. All right. So how do we make U? So this is a 3x3 example, just abstractly. Right, so the first thing we would do is say row 1 of U equals, so here's a question. So what's row 1 of U in terms of row 1 of A? If we don't do any, no row swaps. So let's do no row swaps. Assume no row swaps. So there's a lot of stuff in math where you say, oh, let's take an easier kind of thing, and then that's not a good example because it's the LDU. ALU. They're the same. They're always the same unless there's row swaps. So without row swaps, the first row of U is the first row of A. And if you think about what this is doing, you want 1, 0, 0 times this, so this has to be the case, right? So we're trying to make a really simple combining matrix here. And it always has 1, 0, 0 across the top, or however many zeros. It just says, I want the first row of U to be my first row of A. And then I'm going to have some combination of the first row of U and the second row of U to make the second row of A. So we need to think about that story. So row of U is, so this is assuming no row swaps, is row 1 of A. Now, to get to row 2 of U, we start off with row 2 of A. It's row 2 of A minus L21 times row 1 of A. But we can use this story in here, and we can say this is, well, that's U, right? All right, let's do the third step. Row 3 of U, how do we make that? Well, we start off with row 3 of A. And we subtract L31 times what is now row 1 of U. And we subtract L32 times row 2 of U. So I'll write this out in words, but the way you construct U is you're always using these these revealed rows of U to clean up rows of A. All right, so we're going to invert this in a second, and it's just a few of these guys. So let's put all the A rows on one side. And so the first thing tells us that row 1 of A is equal to row 1 of U. It's definitely something you have to concentrate on. It's a good thing. Row 2 of A, let's leave this here, and we're going to put this guy over on this side. Well, that's row 2 of U plus L21 times row 2 of row 1 of U. And the third one, if we invert that, we'll get row 3 of A is equal to you start with the row 3 of U, and you add L31, let me say, yeah, all right, L31 times row 1 of U. Right, I'm going to put all of this stuff on the other side, plus L32 times row 2 of U. So if you look at this, you can see, and think about how this generalizes, you can see that the rows of A are simply built out of the rows of U. And as we make, the key is that as we make U, we're working our way down, and when we start to, when we work with row 3 of A or row 7 of A, we only use rows of U. That's how we adjust it. That's what the row operations do. Row ops. So let me say, and then I'll move on to another thing, but in words, rows of A are modified by row operations by a whole machinery, a whole Gaussian elimination, by row operations, using only revealed rows of U. Revealed rows of U. Right. And perhaps the last thing to say here, just so you say U and the pivots and the multipliers are all hidden. In A. A is transparently made out of them. Made out of, may not seem it is, but made out of rows of U. Right, so you have to work hard to get to the U, but then to get back to A, it's easy. You've built the whole story. Okay. All right, so what we're going to do, wow. It's very rude. My watch told me to move. It's very sad. What does it think I'm doing? Lecturing is not enough. Okay. Good. Good. Yeah, okay, okay. So let's do transposes. Fun. It's really good. These are really surprising things. Transposes are very surprising things. It's section 2.7. This is on the exam. He said, trying to maintain interest. But no, it's awesome. It's great. Really good. Very surprising. So even when a matrix is not symmetric, we will do something horrible to it to make it symmetric, or to find something that's symmetric inside it. Right? We're desperate for symmetry. Very human kind of problem. Okay. So this is actually a section, if you're referring to the book, section 2.7 in the book. Let's make it the book. I doing? Okay. So it's symmetric matrices and transposes. Transposes. All right, good. Okay. So we've touched on this. Here's a definition. The transpose of A, so the transpose of A, and let's make A, always good to do this, M by N, is written as, it's very surprising how this works, AT, so T for transpose. This one is not hiding anything, truth in advertising there. And this will be an N by M. All right, so we swap the shape. And it's equal to A flipped about the main diagonal. Main or leading diagonal. You'll hear people say that. Turns out to be just a big deal. Oh, yes. Good. So let's have some examples. So let's say 2, 7, 3, minus 1, 2, and 4. There's no real. So we can take transposes of rectangles. That's OK. It's fine. It's still a leading diagonal. Goes straight down. So this is row. This entry here is 1, 1. This entry here is 2, 2. Right? Column 2, row 2, column 2. Yep. So that thing transpose. We'll put a T there. We'll see if you can write that down. Yes. Really, really weird. So we're just going to define these things, and then we'll find out a very basic, fundamental, and again, surprising property. And then a couple of quirky little bits. And then we can do some review. Yep. OK, so rows become columns, columns become rows, however you want to think about it. So this was a 2 by 3. Always good to write that down. This becomes a 3 by 2. The first row ends up coming down here. So 2, 7, 3. You can think of it like that. This row is now the second column. So you can think of it as rows, rows swap with columns. And again, there's this leading diagonal here. Right, let's do a few more. So we've done, so a square matrix is always a simple thing. Transpose, you just swap these guys here, 4, minus 1, 3, 2. What about this one? So this is an example, another example. 3, 7, 2, minus 1. Transpose. Right, 2 by 2 stays as a 2 by 2. 4 by 1, that's a minus 1. 4 by 1 becomes a 1 by 4. Column becomes a row. 3, 7, 2, minus 1. This is a 1 by 4. Where's my thing? 3, 7, 2. This is this where it is? This is a 2. I try. Sorry. Thank you. So then this gives us, we've kind of touched on this, but this gives us our very nice way of writing dot products, and it's built into matrix multiplication. So the dot product, we can now write it. So the dot product, if we have two vectors, let's say we've got u dot v. This is calculus style. Let's say this is in, let's say we have, this is 3D, So we'd have, I don't know, let's say u equals 1, 2, 3, and v equals -1, 0, and -4. Then calculus would be u dot v. It's all in parcel tongue, of course, so it's hard to understand. 1 times -1, these guys, plus 2 times 0, plus 3 times -4. Right, so it's -1, this is that, so it looks like -13. Did I get that right? Fine, great, good for you, calculus. Okay, so, but we have a nicer notation. It's built into the way these things work. And we'll always, so the default is vectors are columns. If no one sort of adds anything to it, you can sort of presume they're columns. So in this case, u dot v for us would be u transpose v. U transpose v. So it's 1, 2, 3, and then -1, 0, -4. It's just built. It's the way it's built in. But we don't just write u times v. That's not going to work for us. Right? U times v doesn't have the right shape. This thing here is with the transpose, is a 1 by 3, and this is a 3 by 1. So these match, matrix multiplication, the 3 and the 3 match, and this is the resulting size, which is a 1 by 1, which we think of as a number. Okay, good, good. -13. So dot products just give you a number, right? So it shouldn't matter which order. What's the transpose of -13? -13 transpose is -13. Good, right. That's fun. So we observe this great little moment here. So we can also do, so we can take this, u transpose v, like this, transpose equals what? So that's kind of a funny little problem, right? We'll get to this. So this is next. But let's think about this. We could also do v transpose u, and that works, right? So v transpose is going to be -1, 0, -4, and then 1, 2, 3 for our u. And so that's -13 as well. So we... This thing? Is it... Oh, it's missing its hat. Sorry. Yeah, thank you. Very important. Here? Yeah, so not quite, right? Because this is the right shape. U is by definition a column vector. Yeah, so we made u look like this here, and v's like this. Because by default they're both column vectors, so we have to flip one if we want to multiply them together. But we know that, so we know this is just a number, it's -13, and we know -13 transpose is -13. So maybe there's something we can do with this. It's two vectors multiplying each other, but it's really two matrices in general. Okay, so if we covered the goodness, I think we have. Okay, well let me say this. I think you should have it. I'm raising an important thing. So, big deal. Let me write it out for you so you have it. The transpose of A will be ridiculously important. That's a mathematical term. Ridiculously important in solving AX equals B, because you think we've done it, but we haven't. Gone as far as we can, and if we're crazy enough, we'll keep going. You know, and everything else, really everything else in linear algebra. It just pops up a lot. Google pops up in Google. Who knows why? All right, we'll talk about that. So that's one big deal. And then also, here's a thing to think about. This character, A transpose, I want to put it in front of you. A transpose A and A transpose will matter a lot. Also huge. Will be huge for us. So, good question. Maybe. Maybe. Not always. Good question. So let's think about one thing about them. So let's do the right thing. M by n. Okay? The shape of this one is m by m because we're flipping it. So they're always well defined. Can't go wrong, right? So if you've got any matrix, you can always take its transpose and stack it here. So this is always good. So this ends up being an n by n. So A transpose A is an n by n. What about the other one? Right, this is m by n here. I'm going to say this whole thing is n by m. So this is good. They match up. And the shape of the whole thing is m by m. It's great that m and n are very different sounding. Okay, m by m. Mathematicians just keep going, right? Phi and psi, let's put those together. Why not have that? Okay, great. Mu and nu, let's do that too. So this is m by n, and this is m by m. So they could be different shapes. They could just be different shapes. They're square, so that's interesting. I think that's interesting. Always square, always well defined, which means you can do it. A ridiculous way of saying they work. Okay? Groovy? Groovy. These guys are really cool. Plus, we've taken a rectangular matrix and made them into square matrices. And square matrices, they're pretty cool guys. Oh, okay, all right. So that's just a little teaser there. Okay. Okay. So let's look at a few properties of the transpose. Okay, this is great. Really bananas. And I think I can skip through the thing at the end, 5 minutes. Yep, sure. Let us dwell on the joy of the transpose. So let's talk about, we need a little bit of notational stuff. So kind of a notation thing here. So when we say A, if we take the ijth entry of Aij, right, then we typically do this, lowercase. It's kind of a standard thing, just like we did L and Lij. So if you break it down into these little terms, then A transpose, the ijth entry of A transpose, how is that related to A? This is a tiny little thing that we have to do. Right, so let's say we have, I just erased it, which is silly, 2, 7, 3, minus 1, 2, and 4. This is A. This is A transpose. 2, 7, 3, minus 1, 2, and 4. So what's the entry, let's say A, 2, 3. Row 2, column 3. Row 2, column 3, this character, right? So that's 4. Where is 4 now? 3, 2. So this is in the 3, 2 position. Right, so one way to say this is you could say A, the 2, 3 entry of that guy is 4, and of A transpose, the 3, 2 entry of that one is 4. So in general, the ijth entry of the transpose is ji. Right? Cool. 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 Okay, so that's a nice tiny little thing, and we can play with that. Let's see. So, okay, great. That's a little piece. Okay, so basic properties. They're very strange things, matrices. Very odd, peculiar beasts. So, addition. Let's say that this is totally fine. We've got m by n, and this one must be the same shape. What's the transpose of that? We're going to add these two matrices together. We could take the transposes and then add them together as well. And that's going to be fine. Is that OK? So equals A transpose plus B transpose. I mean, we could use this notation to explain it. This is an m by m. And this is an n by m. So this should seem pretty OK. Right? As long as you can add these two matrices together, you take the transposes before you add them or after you add them. Cool? Seem cool? Yeah. Yeah. This is should seem easy. Dangerous thing to say, I realize. OK. OK, so let's do the nasty thing. The nasty thing is always multiplication. The nasty business is always in multiplication. So what about this? Let's have A, and we'll make it m by r, and B, we'll make it r by n transpose. Can we relate that to A transpose and B transpose? This is kind of a horrible thing, right? Multiplication, it's a big mass, lots of dot products, and then we're going to flip it. How does this, well, can we express this in terms of, I know I'm running out of time, A transpose and B transpose? Let's do some basic things. So what's A transpose's shape and B transpose? So the shapes. A transpose's shape, it's an R by M. And B transpose's shape is N by R. Park the car in the hover. OK, so how could we combine these things? We can reverse it, right? So we could do it. So this is so in general, this is OK. This will, if this multiplication is OK, because it is, then this is at least doable. So it certainly can't be the case in general that so this is now should be clear. AB transpose cannot equal A transpose B in general, B transpose. Dimensions don't matter. The dimensions don't work. And let's think that this ends up as, this is N by R and R by M. Sorry, M by R, R by M. So the whole shape of this thing is, it's an N by M. These guys match, M by M. And the shape of this thing, it's an M by N, but then it's a transpose. So it's an N by M matrix. So it's the right shape. That's an M. So that's the right shape. It might work. OK. So A, B transpose and B transpose A have the right shape, have the same shape. Let me give you a quick little example. Yep. So here's a little example. Let's just test it out just to see if this is possible. Let's make this A. 2, 3, 1, minus 1. Let's do this, and then minus 1, 4, 3, 1. It's a little test. So let's multiply these guys together, then take the transpose, and then let's take their transposes first. So B transpose times A transpose. So B transpose, minus 1, 1, and then we're going to swap these. So it's going to be 4 and 3. And then and this doesn't prove anything, this is just a little test, right? We've got a suspicion. 1, 3, and the 2 minus 1 are the same. So if you multiply this out, we can just do all these dot products. Make that a minus 1. So minus 2 plus 9. So we've got a 7. And then 8 plus 3 is 11. And then a minus 1 and a minus 3 is minus 4. And then a 4 and a minus 1 is 3. And we still have a transpose. So let's do that. So now we take the transpose. 11 minus 4. OK, so we've taken the transposes here, and now we're multiplying together. Does this work? So minus 2 plus 9 is 7. So that's good. Minus 1, minus 3, so minus 4. And then 8 and 3 is 11. And 4 and minus 1, so 3. So these match. Interesting. 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 OK, that doesn't prove anything. We are emboldened. OK. So we seek a proof for arbitrary A and B. That is crazy. All right, let me try to give you kind of a picture proof, and then I'll do a little algebra one. So let's imagine we have this character here. This is going to be our A. And maybe I'll make this one look not quite as... I want to make that the same, and then maybe these have to match. And then maybe something like that. So let's make this yep. Let's make this A, and this is B. And then we're going to think about the transpose of the whole thing. So let's get to that. So let's take B transpose. So this is a bit wider than it is long. So B, this would be B. So this is M rows, R columns, and then R columns over here, and R rows and N columns. Yep. So we're going to flip this. This is going to be B transpose here, and it's going to have N rows. You have to concentrate on this one. And then R columns. And then this big thing, we're going to flip it this way. So again, it's this flip leading diagonal, like this maybe. And then this is A transpose. So it's going to have R rows and M columns. So let's take one. So it's built out of dot products, right? Matrix multiplication is built out of dot products. So we'll retreat to our dot product story. Let's take one row here. We'll call this one, this is I. And then we'll take a J column over here, J. All right, so the dot product of row I of A and row J, a column J of B is this entry. It's A, B, IJ. That's the definition. It's the ijth entry of A times B. So which entry is this in? So if we now take the transpose, so if we took A, B, transpose, which entry is right? ABIJ, what's the entry in the transpose of the whole thing that matches this? It's this little business here. Yep. So the ijth entry in the product AB is the jith entry in that same product transpose. Transpose just flips rows and columns. So there's that. Now let's locate these characters over here. So this is now this is now the jth row. Right? This one comes over to here. I'm going to draw this over here. It's been flipped over to here. And this is the ith column. This is really not an obvious thing, obviously. Ith column. So the dot product of these two, right, the jth row and the ith column. So let me write that same kind of thing here. The dot product of the jth row of B transpose and the ith row, because it's B transpose, then A, the ith column of A transpose. This is just the definition of the multiplication thing, so it's B transpose, A transpose, and it's Ji. And we know these things are the same, right? These are the same things. It's the same row, and we've just moved these guys over here. So B transpose, A transpose, Ji, A, B transpose. So there's a proof. Or at least a visual kind of proof. So that's not an obvious thing at all. AB transpose is equal to B transpose A transpose. Apologies for that. Little scribbling down there. I think we're running out of time, so I could prove it in a different way. I won't do that. I won't do that. Do that later on. That's another thing to do. Boop-a-doo. Okay, couple of last little pieces to add. Ah, that was bad. All right. So I told you about A transpose A before. So let's go back to those. So back to these curious things, to the curious objects. A transpose A. So we know it's a square matrix. And A transpose. What is the transpose of these? What's the transpose of this thing? Right? We're going to use it. We use the, right, exactly, good. So we use the rule. So in general, it's AB transpose equals B transpose A transpose. So you swap the order and take transposes. So we're going to put this one first. So it's A transpose. And then we're going to have A transpose transpose. A transpose transpose. What's the transpose of the transpose? It's the same, right? We just flipped it back. So this is A transpose A. So what we've shown here is that this blob, which is a square matrix, you take its transpose, you get the same thing. So this is a very special kind of matrix. It's a symmetric matrix. And let's see, and you can show also A transpose is equal to A transpose. So these are symmetric matrices. And so let me finish with that definition, if I didn't write it down. So in general, well, or definition, A is symmetric. Very special word. So this, As we said, there could be all sorts of symmetries, but it's just this one kind of symmetry that matters so much that we call it symmetric. We don't have to add anything else if A equals A transpose. So even if A is not symmetric, we can construct these ones and they'll matter later on. Okay, let me, there are other things we could say. Let me quickly, I'll say one more thing. So later, we'll come back to this. If an inverse exists, the transpose of the inverse is equal to the inverse of the transpose. So this is later, this is something else. Let me now go over here. Okay, so really a weird, very simple little operation, but it has all sorts of goodness associated with it. Let's do this. Okay, as I said, I can just flash through this. You can look at this later on. There's the printout version, right? So you can print it out. Okay, so these videos will be online, possibly. They don't always work, do they? Yeah. We'll see. You can look at these things again. So it's chapter 1, as I said, it's really 2.1 to 2.7. We just did 2.7. You need to, so you need to know, you need to understand how these things work and certainly be able to do them. So I expect everyone to be able to do them. Understanding is the stuff that will really allow you to crank. It's all about AX equals B. We've got m by n. M is the number of equations. N is the number of unknowns. It's always going to be that case for A. We'll always call it m and n. You need to be able to draw the row pictures, the column pictures. Understand what the row picture is. We'll move away from it. How to convert between all of them. We have a matrix picture as well. Simultaneous equations. That's what we started with. And then we just said, no, all right, we're not going to talk about it like that. We're going to have row operations. We go from AX equals B to UX equals C, and then later to RX equals D. We solve by back substitution. Then we talked about elimination matrices and permutation matrices. And we figured out this whole factorization with LU, two triangular systems, LC equals B, solve that, and then UX equals C. And more generally, you need to know this, we talked about today, you could have LDU, complicated thing, that we use LU and LDU. Understand when you have 0 solutions, 1 solutions, infinitely many. There's this little piece, the Gaussian eliminator 9000. You need to be able to do this exactly right, transform it into elimination matrices. I can skip through this, you can look at it later. Understand how L is made, this business here, how we make it out of the elimination matrices, how the LIJs fit in perfectly. Basic matrix multiplication, all that stuff. The commuting doesn't work. How inverses work, you need to be able to do the Gauss-Jordan elimination, definitely a big thing. Inverses work like this. There's some extra stuff. I tweeted this. There's a video explanation at the bottom. Matrix multiplication. And today, transposes. AB transpose equals B transpose A transpose. And there's a couple of other pieces here that you should know about. All right, so that's it. That's a good start. Exam on Thursday. Office hours today, tomorrow. Let's talk about it.